All right, we're just about done here, as long as no idiot comes in and pushes this red button. Slack to the future.
Episode 1. The Pod Couple.
Felix, what did you do? I pushed a big red button that said,
Don't push.
why would you do that?
Duh, because it said don't push.
Well, let's see what the AI says about getting us back home.
Warning. Temporal navigation locked. Engine offline until button pusher demonstrates basic understanding of local historical science.
Local era science? Oh my God, I get it. The time machine must have brought us to an important moment in scientific history. It won't let us leave until you actually learn about it.
I have to learn about it?
Is this some kind of devious plot to get me to do my homework? That's low. You're the one who pushed the button.
Yeah, but I didn't think it would lead to learning.
Irregardless, we need to figure out where we are. Oh, look over there. There's some people.
Yo, Gregor! Time for chanting!
Again? Did we just chant yesterday?
Yes. And the day before that. And the day before that. We chant every day. Is there anything else I can do? Jeez.
You don't like chanting? What, I suppose you'd rather go play with peas?
Actually, I would love to play with peas.
Huh?
Wait, Gregor Peas? Oh my God, that's Gregor Mendel.
Huh? The pea guy? I thought he was green and jolly.
No, he's the father of modern genetics. Let's go watch.
What's he doing? Making a salad?
No, he's counting peas. Specifically, he's counting how many of each peas have certain traits.
Traits? They're peas, Kevin. They don't have personalities. It's not like one pea is introverted and the other pea is a Sagittarius.
Not personality traits, physical traits. Look closely at the plants. Peas have distinct characteristics. For example, the flowers on the plants are either purple or white. The seeds can be bright yellow or green. They can be wrinkled or perfectly smooth.
Oh, I get it. Like a shiny Pokemon.
Yes, but here's the interesting thing. Mendel took a purebred yellow peas, crossed them with a purebred green peas, and do you know what happened?
Wait, what? I thought we were talking about peas. Now you're talking about bread? Pure bread? Like whole wheat?
Not bread we eat, B-R-E-D. When a yellow pea reproduces with itself and makes yellow peas for generations, they're called purebred.
Reproduces with itself? Sheesh. We gotta get that pea plant on Love Island Garden Edition.
They're not people, Felix. Plants often fertilize themselves. It's called self-pollination.
So these purebred pea plants are like the royal families of Europe, where your cousin is also your half-brother.
Let me just get back to the question I asked. Mendel crossed a purebred yellow with a purebred green. What do you think he got?
I don't know, light green peas?
Nope. Every single pea in that next generation was 100% yellow. The green trait completely disappeared.
Whoa, that yellow pea must have totally dominated the green pea if it made it disappear.
It's funny you should mention dominate because Mendel called the stronger trait dominant. When two competing traits are present, the dominant trait is the only thing that you can see as the recessive trait hides away. But then it gets even more interesting. When he crossed those yellow pea plants with each other, the second generation, what do you think happened?
Let me guess. Even more yellow peas?
Nope, the green trait came back. After counting thousands of peas, he realized it wasn't random. It was an exact 3-to-1 ratio of yellow to green.
3-to-1. But why?
Wait, look.
Button pusher has expressed curiosity in subject matter. Progress advances to 50%.
Wait, so showing a little curiosity moved the progress meter?
Of course, curiosity is what drives understanding. Keep this up, and we'll be heading home in no time.
Don't worry, Kevin. I've got this.
Well, let's get back to your question. Why was the ratio 3-to-1? Before we can answer that, we need to look at how early scientists designated the different traits. A dominant trait is represented by a capital letter. Here, yellow is dominant, so it gets a capital Y. A recessive trait is designated by a lowercase letter. Green is recessive, so it gets a lowercase y.
Bro, you do know green starts with a G, right?
True, but whatever letter we use for the dominant trait, we also use for the recessive trait.
Green is stuck with a lowercase y. So G got replaced by Y? That's an L.
An L for G, but a W for Y.
Bruh.
Tough crowd. Well, moving on. It's probably easy to remember that capital Y means yellow and lowercase y means green. But the letters actually represent the genetic code for yellow and the genetic code for green. In biology, we call these code versions alleles, or honestly, you can just call the letter itself the allele. And every single plant inherits two of them, one allele from mom and one from dad.
So wait, that means that the yellow P isn't a single Y, but it's a capital Y, and green would have to be a lowercase y.
Exactly. And because those letter pairs represent the actual genetic code the P carries, we call that the genotype, whereas the physical color you actually see is called the phenotype.
Wait, so that purebred yellow P must be a double capital Y. It got a yellow allele from its mother and a yellow allele from its father.
Spot on. And by that exact same logic, a purebred green pea has to be double lowercase y, inheriting a green allele from mom and a green allele from dad.
Oh yeah, look at all this learning I've done today. Time machine, send us home. Let's go!
Progress advances to 75%.
Looks like there's still a bit more learning to do.
Oh wait, it must be because I haven't solved the 3-to-1 ratio yet.
That's right. And to understand how that 3-to-1 ratio actually works, we need to look at a handy tool called a Punnett Square. A Punnett Square is used to predict all the possible combinations of alleles that an offspring may possess, along with the probability of each combination occurring. List the alleles of one parent across the top, one above each column. Then list the alleles of the other parent down the side, one beside each row. Now fill in each cell by bringing down each letter from the top and bringing across each letter from the side. Now each box in the Punnett Square represents one possible genotype for an offspring.
And because there are 4 equal squares, each one must represent a 25% probability.
Exactly. And in this case, because every genotype is the same, crossing the purebred yellow and the purebred green means 100% of the plants will have this exact genotype.
Wait, this capital Y and lowercase y? We haven't seen this combination before. What's it called?
It's called a hybrid. But full disclosure, scientists use homozygous for purebred and heterozygous for hybrid.
2 words for the exact same thing? That just confirms my suspicion that a shadowy cabal of scientists sits in an ivory tower all day thinking up ways to double our homework.
Just remember, 2 organisms can look completely identical, but one can be homozygous and the other heterozygous.
Yeah, I get it. Like in our example, every possible outcome was heterozygous, but because yellow is dominant, they would all be yellow.
And then remember, Mendel took those hybrid peas and crossed them together, and
Kevin, no need to explain. I got this. First, put the genotype of one parent across the top of the square and the genotype of the second parent down the side. Then, fill in the cells by bringing the letters down from above and sliding them across from the left. If we look at the genotypes, there's a 25% chance for homozygous dominant, a 50% chance for heterozygous, and a 25% chance for homozygous recessive. However, if we look at the phenotypes, yellow dominates in 3 of the 4 cells, leaving us with 3 yellow and 1 green. Boom. 3-to-1 ratio. And that's a wrap.
Felix, you did it! The time machine is back online.
Fully charged. Portal opening in 3, 2, 1.
Oh boy.
Be sure to tune in next time for another episode of Slack to the Future.